Hey there, and welcome. Today we're going to dive into one of the coolest and, honestly, most elegant principles in all of physics, rotational dynamics. It's the science that explains pretty much everything that spins. A planet, a kid's top, and yeah, even that incredible pirouette from a ballet dancer. You've seen this, right? You're watching an ice skater, and they're just completely mesmerizing. They start spinning, they pull their arms in, and then bam! It's like they hit an invisible accelerator. They're suddenly spinning way, way faster. But just stop and think about that for a second. How is that even possible? I mean, there's no engine. She's not kicking off the ice to get a boost. So where does that extra speed come from? That is the exact mystery we are going to solve right now. Okay, so to crack the code on the skater's secret, we've got to learn the basic language of spinning things. And you know what? The absolute best way to get it is to compare it to something we already understand intuitively, just moving in a straight line. So let's put them side by side, the rules for moving straight versus the rules for going around in circles. You're about to see they're basically perfect mirror images of each other. It's kind of wild. In fact, you'll find that for almost every concept we have for linear motion, stuff like distance, speed, mass, there is a direct twin in the world of rotation. It's like a secret code, and we're just about to crack it. So check this out. This table right here is our Rosetta Stone. On the left, you've got your normal straight line motion. On the right, the spinning equivalent. So displacement becomes angular displacement. Velocity becomes angular velocity. But now look at that last row. That's the one. Mass, which is just an object's resistance to being pushed, has a rotational cousin called the moment of inertia. And that concept is the absolute key to this whole thing. So, what on earth is this moment of inertia? I promise, if you can get your head around this one idea, the whole skater mystery just clicks into place. Well, to put it simply, it's how much an object fights back when you try to spin it. Just like mass tells you how hard it is to push something, moment of inertia tells you how hard it is to twist it. But, and this is the crucial part, it's not just about how heavy something is. Unlike mass, which is just a number, moment of inertia depends completely on an object's shape. Specifically, where all its mass is located compared to the point it's spinning around. Think about it like this. When you pull all the mass in tight, really close to the center of the spin, the moment of inertia gets really low. It becomes easy to rotate. But if you take that exact same mass and spread it way out, the moment of inertia shoots up, and it becomes much, much harder to get it spinning. Okay, so we've got the most important piece of our puzzle, moment of inertia. Now we just need to quickly grab the last two tools we need to finish the job, torque and angular momentum. This one's easy. If force is a push or a pull, torque is just a twist. It's what you're doing with a wrench when you turn a bolt. A torque is what you need to change how something is spinning. And last but not least, angular momentum. If linear momentum is the quantity of motion something has, well, angular momentum is its quantity of spin. It's just a way to measure how much rotation is going on. And here is how it all connects in one beautiful, simple equation. The total quantity of spin, which we call angular momentum, or L, is just the moment of inertia, I, multiplied by the spin speed, which we call omega. All you gotta remember is L equals I times omega. Okay, we have all our pieces on the board. We've got moment of inertia, angular velocity, and angular momentum. Now, let's use them to finally unlock the skater's secret with one of the most powerful laws in the entire universe. This is it, the big one, the principle of conservation of angular momentum. And all it says is this: if you're not adding any outside twist, any torque, then the total amount of spin in a system has to stay exactly the same. It can't just appear or disappear. It's conserved. So what does that mean for our equation? It means that L, the total spin, has to stay constant, which means that I and omega are locked together in this delicate little dance. If one of them goes down, the other one has to go up to keep the total the same. Let's actually watch this happen. On the left, see how the person's holding weights way out? Their mass is spread out far from the center, so their moment of inertia, I, is huge. To keep the total momentum the same, their spin speed, omega, has to be slow. But now, watch what happens when they pull those weights in. Their I gets smaller, so their omega has to get bigger. They speed right up. And we see the exact same thing with a high diver. They jump off the board all stretched out, then pull into a super tight tuck. By doing that, they slash their moment of inertia. And what happens? Their rotational speed shoots through the roof. letting them get in a few extra somersaults before they hit the water. And that brings us right back to our dancer. See, it's not magic. It's just really, really cool physics. When her arms are out, her moment of inertia, that's the I, is high, so her spin speed, the omega, is low. The second she pulls her arms in, she's just rearranging her mass. She makes her moment of inertia tiny. And because that total angular momentum has to be conserved, her spin speed has to skyrocket to make up the difference. And that's what's so amazing about this. This isn't just a neat party trick for dancers and divers. This fundamental law, the conservation of angular momentum, is universal. It's what governs the spin of planets as they go around the sun, the rotation of entire galaxies, and even the ways stars collapse. Which actually leaves us with one last little thing to chew on. Think about this. If the ice at Earth's poles melts and all that water spreads out toward the equator, that changes how our planet's mass is distributed, right? So based on everything we just learned, what do you think that would do to the length of our day? Something to think about. Thanks for tuning in.